Neptune should be frozen and silent. It should be calm. It should be dead. But it isn't. Instead, it is one of the most violent worlds in our solar system, and something invisible is driving it. Neptune orbits nearly 4.5 billion kilometers from the Sun, drifting in a region where sunlight arrives faint and diluted. At that immense distance, solar energy is only a fraction of what inner planets receive. By simple logic, such a world should be frozen into quiet stillness, a distant, inactive sphere barely stirred by external forces. The expectation is straightforward. Less sunlight means less atmospheric motion, less turbulence, less power. And yet, Neptune defies that expectation in dramatic fashion. It hosts the fastest winds ever recorded in the solar system, with speeds exceeding 2,000 kilometers per hour. These are not gentle breezes shaped by weak sunlight. They are violent, supersonic currents tearing across a planet that should, by all conventional reasoning, be calm and dormant. The contradiction is striking. How does a world so deprived of solar input generate such ferocity? The answer cannot lie in sunlight alone. Neptune radiates more energy than it receives, meaning something deep within the planet is driving this activity. Internal heat, trapped since its formation billions of years ago, slowly escapes outward. That internal energy feeds atmospheric instability, creating powerful convection currents and complex wind systems. Instead of being powered from above by the sun, Neptune is energized from below, an inside-out engine running in the darkness. That is where the mystery truly begins. Neptune breaks the rules we expect planets to follow. It reminds us that distance does not equal weakness, and that some of the most extreme environments in our solar system are powered by forces we cannot see. In the dim outer reaches of space, far from the sun's dominance, a hidden engine continues to roar, challenging our assumptions about how planets are supposed to behave. Unlike Earth, where sunlight drives most atmospheric and surface processes, Neptune operates under a very different energy balance. Solar radiation at its distance is faint and diluted, far too weak to account for the planet's violent winds and turbulent storms. Yet measurements show that Neptune radiates significantly more heat into space than it absorbs from the sun. That imbalance points to a powerful internal source, an engine hidden beneath immense layers of hydrogen, helium, and exotic forms of water, ammonia, and methane ice. Deep below its visible clouds, extreme pressures and temperatures create conditions unlike anything on Earth. The planet's interior is not a quiet, frozen core, but a dynamic environment where heat slowly migrates outward. Much of this energy is believed to be primordial, leftover heat from Neptune's formation over 4 billion years ago, when gravitational collapse compressed material and generated enormous thermal energy. That heat, trapped within the planet's massive structure, has been leaking into space ever since. However, primordial heat alone may not fully explain the intensity of Neptune's atmospheric behavior. If it were simply cooling at a steady rate, we might expect a gradual decline in activity. Instead, Neptune remains astonishingly energetic. This raises deeper questions about ongoing internal processes. Could there be complex convection patterns in its mantle-like layers? Could phase transitions within its exotic ices be releasing additional energy? The idea of a simple, fading heat source may be too narrow to capture what is truly happening inside. What if Neptune is not merely a planet slowly losing its birth heat? What if it is still dynamically evolving, restructuring internally, redistributing mass, and generating energy through mechanisms we only partially understand? In that case, Neptune is not a dying ember at the edge of the solar system, but a living system in motion. Its internal engine may not just be a relic of the past. It could be an active force shaping the planet's present and future in ways we are only beginning to imagine. Neptune's atmosphere is anything but shallow. It extends thousands of kilometers downward into regions where pressure rises to unimaginable levels. What we see as a smooth blue exterior is only the uppermost veil of a vast and complex structure. Methane in the upper atmosphere absorbs red light and reflects blue, giving Neptune its striking color. But beneath those visible clouds, deeper layers likely contain superheated mixtures of water, ammonia, and methane compressed into exotic states of matter. Under such extreme pressure and temperature, chemistry behaves in unfamiliar ways, creating environments that blur the line between gas, liquid, and something entirely different. In those crushing depths, laboratory experiments suggest that methane molecules could break apart, freeing carbon atoms that crystallize into tiny diamonds. These solid crystals, heavier than their surroundings, would then sink deeper toward the core in a phenomenon often described as diamond rain. Imagine literal diamonds falling through a vast planetary ocean of dense, electrically conductive fluid, an alien weather system operating far below the clouds we can observe. As these carbon crystals descend, they would release gravitational energy, potentially contributing additional heat to Neptune's interior. That raises a compelling possibility. Could this hidden rain of diamonds help sustain the planet's internal heat flow and, in turn, fuel the extreme storms raging above? Neptune's magnetic field is wildly tilted and noticeably offset from the planet's center, creating a magnetic structure that behaves far more unpredictably than Earth's relatively stable alignment. Instead of a clean, centered dipole field, Neptune's magnetism appears distorted and dynamic, suggesting that its source lies in an unusual internal layer rather than a simple metallic core. Deep within the planet, scientists believe there may exist a vast region of electrically conductive superionic water, formed under crushing pressures and extreme temperatures. In this exotic state, water molecules break apart, locking oxygen atoms into a rigid lattice while hydrogen ions move freely through it, producing powerful electrical currents. Since electrical currents generate magnetic fields, this chaotic, off-center internal dynamo could explain Neptune's strange magnetic geometry. If so, the instability of that magnetic field may not remain confined below the surface. It could interact with charged particles and subtly influence atmospheric behavior above. This raises a profound possibility. Neptune's invisible driving force may not be purely thermal, but partly electromagnetic, adding yet another hidden engine to the mystery of this distant and dynamic world. Neptune's largest moon, Triton, is no ordinary satellite. It orbits in a retrograde direction, a strong indication that it was likely captured rather than formed alongside the planet, and that violent gravitational event may still echo through the system today. Because Triton moves opposite to Neptune's rotation, their gravitational relationship is complex and slowly evolving, creating long-term tidal interactions that can generate internal stress within the planet. Over immense stretches of time, even subtle gravitational tugs can produce friction and heat inside planetary layers, redistributing energy and potentially influencing convection deep below the clouds. Tidal forces are known elsewhere in the solar system to stir interiors and sustain activity, so it is plausible that Triton's steady pull may be quietly agitating Neptune from the outside, contributing in small but persistent ways to its internal dynamics. In that sense, Triton may act as an invisible hand, exerting a silent gravitational tension that helps shape the hidden power driving this distant and enigmatic world. If you're enjoying this deep dive into the outer solar system, subscribe now. We explore the most mysterious and extreme worlds in space every week. And trust me, this is just the beginning. In 1989, when Voyager 2 flew past Neptune, it captured images of a colossal storm system known as the Great Dark Spot, a swirling vortex comparable in size to Earth and reminiscent of Jupiter's Great Red Spot. At the time, scientists assumed it might be a long-lived atmospheric feature, perhaps a stable hallmark of Neptune's climate. But when telescopes later turned their gaze back toward the distant planet, the massive storm had vanished without a trace. In its place, new dark spots appeared elsewhere, only to fade again over time. Unlike Jupiter's persistent storm systems, Neptune's tempests seem to form and dissipate unpredictably, suggesting a restless and shifting energy source beneath the clouds. These disappearing storms reveal that Neptune's atmosphere is not governed by steady, surface-level forces, but by unstable dynamics rising from deep within. This is not a frozen, passive ice giant drifting in silence. It is a world driven from the inside out, where hidden engines constantly reshape the face of the planet. Neptune receives less than 1% of the sunlight that reaches Earth, a faint trickle of energy at the far edge of the solar system. By every simple expectation, it should be a quiet, frozen giant, dim, slow, and largely inactive. And yet it remains astonishingly alive. Its atmosphere churns with violent storms, its winds reach extreme speeds, and its internal heat continues to radiate into space. The deeper we study this distant world, the more it behaves like a planet that refuses to cool down, as if some hidden mechanism keeps reigniting motion beneath its blue clouds. This behavior challenges our current understanding of planetary physics. Traditional models often link atmospheric intensity to solar input, but Neptune breaks that pattern. Its energy appears to rise from within, not from above, suggesting that internal processes, convection, exotic chemistry, gravitational interactions, play a far greater role than once assumed. Each new observation forces scientists to refine their theories, because Neptune does not fit neatly into established categories. It is an ice giant that behaves, in many ways, like something far more volatile. And here lies the unsettling truth. Humanity has visited Neptune only once, during Voyager 2's brief flyby in 1989. Every image, every measurement, every major discovery came from that single encounter. Everything else we claim to understand is derived from distant telescope observations and theoretical models. Much of what we think we know about Neptune remains hypothesis, educated, carefully calculated, but still incomplete. The planet that shouldn't be so alive continues to guard its secrets in the darkness, reminding us how much of the solar system remains unexplored and uncertain. If Neptune can remain this active despite receiving only a fraction of the sun's energy, it forces us to rethink how we evaluate distant worlds beyond our solar system. For decades, astronomers often estimated a planet's potential activity based largely on its distance from its star. But Neptune suggests that internal heat, complex chemistry, magnetic dynamics, and gravitational interactions may be just as important, perhaps even dominant. If a planet so remote can sustain violent winds and internal energy for billions of years, then stellar distance alone cannot define whether a world is dormant or dynamic. Across the galaxy, ice giants appear to be extremely common. Many of the exoplanets discovered so far fall into size categories similar to Neptune. This raises a profound possibility. Perhaps worlds like Neptune are not unusual outliers, but representatives of a dominant planetary type. And if that is true, then beneath thick, opaque atmospheres scattered throughout the universe, invisible internal engines may be running everywhere, generating heat, magnetic fields, and atmospheric motion far from the light of their stars. Neptune may not just be a mystery. It may be a preview of how active and complex many distant worlds truly are. Neptune is not silent. It is not frozen. It is not passive. It is alive with invisible power. And we've barely scratched the surface. If you want to uncover more cosmic mysteries, subscribe and join us in exploring the unknown. Because the darkest planets may hide the brightest secrets.